Hello students, and welcome to our lesson today. We are going to have Analogue Electronics 2, and our unit code is BEG3203, and it's lesson 1. And our topic is operational amplifiers. That gives the outline of our topic. We shall look at definition of operational amplifiers. We also look at the op-amp parameters, the ideal characteristics of operational amplifiers, and operational amplifier applications. We start by defining an operational amplifier. It's usually abbreviated as an op-amp. That is the short form for operational amplifier. And it is a fundamentally voltage amplifying device which is designed to be used with some external feedback components such as resistors, capacitors between its output and input terminals. It can also be defined as a high gain, high input impedance amplifier which can amplify signals between 0 to a little beyond 1 megahertz. So here the feedback components determine the function of the operation of the amplifier, and by virtue of the different feedback configurations, whether resistive, capacitive, or they can be used in combination, the amplifier can perform a variety of different operations, and that gives rise to its name, operational amplifier. So operational amplifiers form the basic building block of the analog electronic circuits. Now this is the operational amplifier simple. Remember I said that the short form of operational amplifier is the op-amp. So we are going to use that term frequently. And to start with, as you can see in my op-amp symbol here, the diagram there has 3 terminals. But basically, an operational amplifier has a minimum of 5 terminals, which of one, we have the inverting terminal, and it is marked with negative or a minus sign. We also have the non-inverting terminal, which is marked with the plus sign. We also have the output terminal here, and because I'm saying it should have a minimum of 5 terminals, for the sake of simplicity of diagrams when using the op-amp, those 2 terminals, one which is here, the positive bias supply terminal, and also the negative bias supply terminal is usually at this particular point and this point. So that makes a minimum of 5 terminals. But practically, you will also find that there are other terminals. For example, the offset terminal, which is also in that device. So those are basically the terminals and the symbol of an operational amplifier. Now we look at the op-amp parameters. The op-amp parameters, and the very first one is our input offset voltage. When talk about input offset voltage, this refers to the error voltage that must be applied to the inputs of the operational amplifier to null or to make 0 the quiescent output voltage. Practically, for an op-amp, you'll find that even when you measure the output, you may realize that a small voltage or a false voltage is appearing at the output, despite that the fact that at the input there are there is nothing, or there is no signal that is applied. So that is actually that is actually what causes or makes it a must before you use it to apply an input offset voltage. This input offset voltage is applied to the input to make 0 the output voltage. Output voltage, which may be false, may be due to noise, and it must be made 0, or it must be nulled. So the smaller the value, the better the input terminals are matched for any given operational amplifier. Parameter number 2 is the input offset current. This is defined as the difference between the two input currents of the operational amplifier. Remember, we said that we have two input terminals, that is the inverting and the non-inverting terminals. So op-amps are usually fabricated using the monolithic IC type of construction, which actually produces well-matched devices for input stages and other stages. So, and that usually utilizes an identical geometry for a pair of devices diffused at the same time on the same chip. But despite the fact that they are fabricated using such a technology which can produce well-matched devices, there is always a mismatch which gives rise to input offset voltage. For example, you may find that there is a particular transistor, the same manufacturer, the same number, but when it comes to the base current, you find there is a deviation. So the same occurs with op-amps, because basically inside the op-amp is equivalent of, at the input terminals, we have equivalent of transistors, and there must be a current. There must be a current to bias. So the difference between the two input currents is what we refer to as input offset current. So the smaller the current, the better the op-amp. We also have input bias current. This is, remember when we were talking about the input offset current, we said there must be a current that flows. So that difference. So input bias current, we are actually taking the difference, the average, not the difference. Input offset, we are taking the difference to get the offset bias current. But input bias current, we are actually taking the average. It is the average of the current that flows in the inverting and the non-inverting terminals of the operational amplifier. Basically, if we have, we were to talk of IB, maybe in the inverting terminal, and IB in the non-inverting terminal, then we are talking about the input bias current, I, you can call it I, is equals to IB plus IB on the negative terminal, then divide by 2. That will give us the input bias current. That will give us the input bias current. And we're saying the smaller the possible, and the smaller the current, the smaller the possible unbalance. Next, we have common mode rejection ratio, which is usually abbreviated as CMRR. CMRR is defined as the ratio of the differential voltage gain to the common mode voltage gain. Now, when we are talking about differential gain, we have this is our op-amp symbol with the non-inverting input and the non-inverting input. So basically, if we have this is V1, V2, the amplifier, if the amplifier gain is A, then it means that our output voltage here is equals to the gain multiplied by VID, whereby our VID is equals to, this is V out, whereby our VID is equals to V2 minus V1. So when we get, we are talking about differential gain, which can be denoted as AD, we are saying it's our V out over VID. And that's why we are saying V out is equals to AD minus VID. So this is our differential gain. It's gain that we get when we amplify the difference of the input voltages between these two terminals. We get AD. That is the differential gain. Common mode gain is realized when the two inputs have similar voltages. So we can have maybe at the inverting input V1, at the non-inverting input V2. So that common voltage, when it is amplified, it gives us what we refer to as the common mode gain, ACM, common mode gain. So the common mode gain, we are talking about a CMRR, which is our common mode rejection ratio, is equals to AD over ACM, whereby our AD is the differential gain, ACM is the common mode gain. And we've said that this is as a result of amplification of voltage, amplification of the differential voltage at the input. ACM is the gain, which results as amplification as a result of amplification of the common voltage appearing at the inputs of the operational amplifier. We can see here we have the magnitude. It's written, and then it has a magnitude, means that our differential gain here can attain either a negative value or a positive value depending on which of the two inputs is high. So if, for example, V1 is high, it means that our VID will be a negative. If our V2 is higher than V1, it means that our differential gain will be a positive, and therefore our value here will gain a positive. So in case we have a negative, then that magnitude there takes care of that. We also say that the higher the CMRR, the better the input terminal matching, and the smaller the common mode output voltage. Remember, we've said that with a common mode signal gives our ACM. Differential gain gives our gain as AD. And our amplifier should actually give a higher differential gain and should give a very small common mode gain. So if we may take, for instance, noise appears at the two input terminals. So if noise, if for example we don't have noise here, it means that our ACM will be very small, because noise is a common signal to the two input terminals. So if, for example, our noise was 0, then it means that this value will also be low. And we're saying the higher the CMRR, the better is the input terminal matching. That shows the ability of the operational amplifier to reject common mode signals such as noise and to only amplify the differential signals. So the other parameter that we look at is the slew rate. The slew rate. Slew rate is defined as the maximum rate of change of the output voltage per unit time, and it is expressed as volts per microsecond. So therefore, SR, which represents our slew rate, is equals to dV V out. This represents our output voltage over dt. This is a change in time, and we are talking about maximum rate of change, and we express that in volts per microsecond. We express that in volts per microsecond. That means, if, for example, you have it means that, if, for example, this is your op-amp, and you're given an input here signal, either in the inverting or the non-inverting. The signal before it can, if this is our, for example, our signal that appears at the input, at the instant you are applying, or rather the positive going part is appearing at the input here. At the output, you may not be having the same. There will be a delay between the time which you apply the input and the time that you get your output. And that delay is actually what we are referring here to, dt here. There will be a change in time. So here is your output. So the rate at which your output is changing as you apply your signal is what we refer to as slew rate, slew rate. Slew rate indicates how fast the output of the op-amp can change in response to changes in the input frequencies. Remember, your input here can be a sinusoidal signal, can be a square waveform, etc. So the rate at which the output is changing is what we are referring to as the output. So for a sinusoidal signal, if the signal slope is greater slew rate, distortion occurs. And I will just illustrate how slew rate occurs with sinusoidal signals. Remember, our output, we are saying, it is changing. Changes. If we had applied an input here, we expect it to change as time goes by. Assuming this is our omega t, this is our V out. We'll expect our output to be changing in such a manner. So you may have a signal of a frequency like this. So if this is our input, V in, then we have, this is omega t. If we have that as our input voltage, and if the slope of the resulting output will be less or equal to slew rate, if the slope of the output will be equal or less to slew rate, then we will get an exact replica of the input voltage, but in the amplified fashion, which is not distorted, amplified, but in a replica of the input voltage, but not distorted. This being omega t, this is being V out. That is when the slope is less or equal to slew rate. But for example, if the input sinusoidal signal, for example, has a very sharp high frequency such that you have something like that, this is V out. If you are getting a V out, you are amplifying a signal with high frequency, you may find that the output will not, the slope of the output voltage signal, or rather the signal frequency, will not be in line with the slew rate. In such a case, the output will be forced to follow the slope of the slew rate, such that if this was to be our output and this was to be our slope of slew rate, then you may find that instead of getting a sinusoidal, a clear sinusoidal waveform at the output, you get something that is rectangular because the signal is trying to follow the slope of the slew rate. So for this one is slew rate is less, less than the slope. Or you can write slope is greater slew rate. slope is greater slew rate. So in such a case, you get a distorted waveform, a rectangular waveform, which means our output will not be a replica of the input. Normally, for each and every amplifier, the slew rate is usually specified. Things like also the input offset current, input offset voltage, input bias current are usually specified for any given operational amplifier. Before we go to the ideal op-amp and its equivalent circuit, would want us to look at something small, still on slew rates. Can do one or two examples on slew rates. But before then, if, for example, we assume a high frequency signal with a large amplitude, and with a sinusoidal input is applied to our op-amp of a voltage follower. Voltage follower does not have gain. The gain is usually 1. So we assume that we apply a high frequency signal with a sinusoidal input and a large amplitude to our voltage follower. Then the equation for the input voltage will be expressed as Vin is equals to Vm sine omega t. Remember, it's this is the instantaneous voltage at any given point of the input signal. So our input voltage will be given as Vm sine omega t, whereby Vm is the maximum voltage. And because we are talking about a unit follower, which does not have voltage gain, or rather Vin is equals to Vout, then our output voltage will be expressed in similar manner, such that our Vout will also be equal to Vm sine omega t, will be expressed as Vm sine omega t. So with no slew rate limitations, we are saying the output will be expressed as the same as the input. So if this is our input, if this is our output, we can now get the rate of change of the output. That is dV out over dt will be equals to Vm. This becomes cos omega t. The rate of change of the output voltage will be given to by Vm cos omega t. Now, because when you talk about slew rate, we are talking about maximum rate of change of the output voltage by volts per microsecond. We can look at this expression and see that our rate of change will be maximum. When this expression is Vm, then cos cos 0 will be maximum when Vm is equals to, will be maximum when, there is something I omitted here. This is omega. When you differentiate this, you get omega Vm cos omega t. So we are saying dV out over dt will be equal to omega Vm cos omega t. So we are saying for this one to be maximum, then the cosine of omega t must be 1. So this will be maximum when this value, omega t, is equals to 0. You know, cosine of 0 is equals to 1. So that we can express our dV out over dt maximum is equals to omega Vm. That will be the maximum rate of change of the output voltage. That will be the maximum rate of change of the output voltage. But then we know that from the slew rate definition that slew rate is defined as the rate of change of the output voltage per unit time. So we can substitute here and say, but SR is equals to omega Vm. Our slew rate is equals to omega Vm, and this is volts per microseconds. That is volts per microseconds. So if SR, or rather our slew rate, is equals to omega Vm volts per microseconds, this can be rewritten as omega we know is 2 pi f Vm. Then this is volts per, sorry, this is from the previous here, this was supposed to be per second because we had divided with dt, so this is per second. So that when we come here, it still remains per second, so volts per second. So that we can say slew rate is equals to 2 pi f Vm volts per microsecond. Because we are talking of volts per microseconds, we can divide this by 10 raised to 6 and then make it volts per microseconds. Remember here when we are dividing here, dv out over dt maximum is equals to omega Vm. This is volts per seconds because we are dividing actually with seconds here. Time output is being expressed as the rate of change of the output per second here. So volts per second. So, but we know this one is equals to slew rate, which can be also written as omega Vm volts per seconds. So if slew rate is omega Vm volts per second, can also be rewritten as 2 pi Vm, where Vm is maximum voltage or peak voltage, volts per second. And because we are also talking about microseconds, we can also express it this way as 2 pi Vm volts per microseconds. Alternatively, you can also say SR is equals to 2 pi Vm times, this one you bring it up here, 10 times 6 volts per microseconds. Now, that is what is slew rate, and for any given operational amplifier, it's usually specified in the manufacturer's data sheet, plus those other parameters like the input offset voltage, the input bias current, etc. All the parameters are usually specified. Now, I want us now to look at just a few examples on slew rates. Can look at example number 1 here. Example number 1. We are told that an inverting 741C amplifier, 741 is an operational amplifier, must have a flat frequency response of up to 40 kilohertz. What maximum peak-to-peak input signal can be applied without distorting the output? What maximum peak-to-peak input signal can be applied without distorting the output? You're given the slew rate for the 741 is usually 0.5 volts per microseconds. Then you are also given the amplifier gain as, 10. So the question here is to determine maximum peak-to-peak input signal that can be applied without distorting the output. Remember, the output, you want to get a replica of the input. So you first write down what you're given here. The gain is equals to 10. You're also given the slew rate, which is equals to 0.5 volts per microseconds. You're also given the frequency is 40 kilohertz, which can also be written as 40 times 10 raised to 3 hertz. What else are we given? Now we can now write the formula for slew rate and see, once we substitute this value, what do we get, because we are taught to get the input. So slew rate is equals to 2 pi f Vm over 10 raised to 6. This is volts per microseconds. That is volts per microseconds. That is volts per microseconds. We've given the value of slew rate, which is 0.5. We've been given the value of the frequency. So what we don't have is Vm. And remember, this Vm is the peak voltage at the output. So we can make Vm the subject of the formula. We can make Vm the subject of the formula and say we can make Vm the subject of the formula and say SR so we are saying we make Vm the subject of the formula. So we have Vm is equals to slew rate. This will bring this side. We have 2 pi f, then times 10 raised to 6, like that. So we have Vm is equals to 0.5 times 10 raised to 6, then divided by 2 pi times 40 times 10 raised to 3 hertz. Those are hertz. So that once you work out this, you will get 1.99 peak. So our Vm is equals to 1.99 peak. 1.99 volts, but this is peak. Our question is asking, what is the maximum peak-to-peak input signal? We are given the gain. We have obtained our Vm. So to get the input, we say gain is equals to V out over V in. Because we have gotten our peak voltage, we can get also peak voltage for the input. So our gain is 10. So we say V in is equals to V out divided by our gain, which is also equal to 1.99 over 10, which gives us 0.199. So this is our V in but peak. That is our V in but peak voltage. Our question is asking peak to peak. So when you are talking about peak, we are actually from here up to here is peak. From this particular point, 0 to maximum here, that one we usually call it peak. But from here up to here, that is what we refer to as peak to peak. So to get peak to peak, now you get your V in that you have gotten, then you multiply by 2. You get 0.398 volts. So that is your peak to peak input voltage. That is your peak to peak input voltage. So our peak to peak input V in, after you you work out, you get 0.398 volts. That will be your peak to peak after you multiply. We can also look at another example still. Example number 2. We are also given another amplifier here, an inverting amplifier with a gain of 50. And we are told that the variable sinusoidal input has a variable frequency and a maximum amplitude of 20 millivolts peak. Determine or find the maximum frequency of the input. Find the maximum frequency of the input at which the output will be undistorted. And we assume that the amplifier is initially nulled. We are given slew rate of the 741C is 0.5 volts per microseconds. So what you do is first you list down whatever you've been given. You've been given gain is equals to 50. You've also been given the input. Input V in is equals to 20 millivolts. It's equals to 20 millivolts peak. This is a peak value. We also given the slew rate, which is equals to 0.5 volts per microseconds. Now you come here and write the formula for slew rate, which is equals to 2 pi Vm, 2 pi F Vm, then over 10 raised to 6 is volts per microseconds. So we've been given V in. So because we're given V in and the gain, it's possible that we can be able to obtain our Vm, which is our peak output voltage. So here we can say V out peak is equals to 50, the gain times our V in, which is 20 millivolts. This gives us 1,000 millivolts, of which can also be written as 1 volt. That is 1 volt. Our area of interest here is to find the frequency. So we have determined our value of peak output voltage. We know our slew rate, so we get now the frequency. It's the one that we've been asked to calculate. So we say, we disarrange just this formula and say slew rate. We say frequency is equals to slew rate, you multiply by 10 raised to 6, then divided by 2 pi Vm. So substituting these values here, 0.5 times 10 raised to 6 over 2 pi, then times 1 millivolt. Our frequency here we get 79,577. That is our frequency in hertz. You can as well express it in kilohertz. So if you express it in kilohertz, it will be 79.6 kilohertz. That will be the maximum frequency of the input at which the output will be undistorted. That will be the frequency at which the output will be undistorted. Now, next we look at the ideal operational amplifier. Remember, when I was beginning, I mentioned that the operational amplifier has a minimum of 5 terminals. I think in this diagram, they are well highlighted. We have the inverting input. We also have the non-inverting input. We have the positive supply bias terminal and the negative bias supply terminal and the output. So this presents the equivalent circuit of an operational amplifier, an ideal operational amplifier. When talking about ideal, is a perfect one. A perfect one. Here, as you can see inside here, we have our Z in. This is input impedance. In the equivalent circuit is represented as this, and it is usually very high for an ideal operational amplifier. such that no current, such that a very small current will flow in the input terminals. We also have the equivalent Z out, or rather output impedance of the operational amplifier. So it's usually a very low output, because if a load was to be connected at the output here, then Z out would appear connected in series. But it is usually very small, such that it makes little effect on the output voltage of the operational amplifier. Now we look at the ideal characteristics of an operational amplifier. An ideal operational amplifier is actually one that does not have any kind of feedback circuit in it, or rather there is no fraction of output voltage or signal taken back to the input. When you talk about feedback, is whereby a signal from the output is sampled and taken back to the input. So with such an op-amp, it doesn't have feedback. So the characteristic number one, we have infinite open loop gain. Infinite open loop gain. An operational amplifier is an amplifier that has a very high gain. It's a very high gain. So when it is connected without any feedback, it usually has it's actually an ideal, and we say it usually has a infinite open loop gain. That means that it can amplify any signal. It can amplify any signal appearing at the inputs, any signal of any frequency appearing at the input. We also have characteristic number two is infinite input impedance. And when talking about infinite input impedance, that is the ratio between the input voltage to input current. And because of the high impedance, we know that the amplifier will have a very or negligible current. So obviously the input will be high, but for an ideal, we usually say it has infinite input impedance. That is the resistance which is measured. The input impedance is the resistance which is measured between the inverting and the non-inverting terminals of the amplifier. So with such an amplifier, no current flows from the source supply into the amplifier's input, and therefore the device will not make any power requirements or demands on the signal source because of because no current flows from the source supply into the amplifier's input. So there would be no demands on power. So, but practically, op-amps usually have a very small leakage current from a few amps to from a few picoamps to a few milliamps. Then we have the output impedance. The output impedance of an ideal operational amplifier is 0, and it's assumed to be 0. That is, it acts like an internal voltage source with no internal resistance, so that it can supply as much current as necessary to the load. Remember, we, from the diagram, I indicated that that output resistance is connected. If you are to connect load, they will be in series. So if the resistance is, we are talking about 0, it means there will be no current, there will be no drop, and therefore we get maximum output from the output terminal. So that means that V0 is not dependent on the output resistance. But practically, this is for we say output impedance is 0 for an ideal, a perfect operational amplifier. But for a practical amplifier, it usually have a finite resistance that can be measured, and it is usually very small, that cannot make any much effect on the output or voltage of the operational amplifier. Then we also have number 4. It's also another ideal characteristic. We say it has infinite bandwidth. Infinite bandwidth means that it can be able to amplify any signals with any frequency appearing at the input. So we're saying that it has infinite frequency response. Any signal with frequencies appearing at the input, that's from DC to a little beyond 1 megahertz, can be able to amplify. It can amplify any frequency signal from DC to the highest AC frequency, so that it's therefore assumed to have an infinite bandwidth. But with real operational amplifiers, the bandwidth is usually limited by gain bandwidth product, which is equal to the frequency where the amplifier's gain becomes unity. Another ideal characteristic is infinite slew rate. Infinite slew rate. I'd explained what is slew rate. That is the rate of change of the input, the rate of change of the output voltage with time. And when it means it has infinite slew rate, it means that the delay between when the signal is applied and when it appears at the output is negligible, and therefore having an infinite slew rate. Then next we have another ideal characteristic is infinite common mode rejection ratio. We had mentioned that common mode rejection ratio is the ratio between the differential gain and the common mode gain. So remember, the significance of this is to shows that the amplifier, the operational amplifier, is able to reject common mode signals. So if a common mode signal is small, then it means that CMRR is high. So for an ideal operational amplifier, it usually has infinite common mode rejection ratio. Now, we look at the ideal voltage transfer curve of the op-amp. Here, output of the offset voltage is assumed to be 0. And when you look at this curve, you can see these it's actually V out, or the output voltage plotted against the differential voltage, this differential voltage. So if it were to be plotted for any given operational amplifier, then you can see that there, as you increase the differential voltage, V out is increasing, and it increases until it reaches a point where it remains constant, There is a direct increase in voltage as you increase the differential voltage, but once it reaches the positive saturation voltage, it becomes constant. Remember, we have said that an operational amplifier has infinite gain, which means it can amplify, but you cannot expect to get maybe 1,000 volts in a very in such a device. So what limits the voltage gain or the output voltage of operational amplifier is actually the positive saturation voltage and also the negative saturation voltage. The supply voltages limits the output voltages limits the output voltages of the operational amplifier. So if, for example, VCC and VEE, the positive and the negative supply voltages were, for example, 5 volts, and you apply to the inputs increasing voltage, then the output will be changing until it reaches it goes somewhere near the positive saturation and also negative saturation voltage. If the signal is on the negative side, if it is on the positive side, it goes up to the positive saturation voltage. So that is the ideal transfer curve of the voltage curve of the operational amplifier. Now we look at operational amplifier configuration. We usually have two configurations, that is the open loop configuration and closed loop configuration. With open loop configuration is where we don't have any feedback, and in closed loop configuration is whereby we have some sort of feedback. So under open loop configuration we have the differential amplifier. We also have the inverting amplifier and the non-inverting amplifier. I can start with the differential amplifier. So here we have our non-inverting terminal and our inverting terminal is negative. So in a differential amplifier we are applying signals to, we apply our input signal to both terminals here. And then we have our V out. So this being V1, V2, then the difference in the two voltages is our differential voltage, Vi. Then our gain being A, then our V out here will be expressed as gain times our VID, where our VID is our differential input, the difference between two inputs. So that is the differential configuration of the differential amplifier. Next we have the inverting amplifier. Here you apply the signal, can apply the signal. The inverting, you apply the signal to the inverting terminal. This is the inverting terminal. So you apply your signal there, and then the non-inverting terminal you ground like that. That forms the open loop configuration of the inverting amplifier. Next, you can also have the non-inverting. The non-inverting here, you apply your signal to the non-inverting terminal. This is your signal here. And then the other terminal is grounded, so you get your outputs. So if this is, for example, V1, this is our gain, our output here, V out, will be equal to A multiplied by V1. For this other one, if our input here in the inverting terminal was, let's say V2, then our output here will be, and our gain is A, our output here will be equal to A multiplied by V2. So those are the configurations of the open loop amplifier. So we've said in the differential amplifier you apply the signals, one signal in the inverting terminal, another signal in the non-inverting terminal. In the inverting amplifier, you apply your signal. You apply your signal in the inverting input, and then you ground the positive. On the non-inverting, you apply your signal in the non-inverting terminal, and you ground the negative. Before we can move forward, maybe I can explain what is the inverting and the non-inverting. If, for example, you apply your signal here on the inverting, the negative is the inverting, a sinusoidal signal like this. At the output, you get an amplified fashion, but which is out of phase with the input, like this. You can see the signal as being inverted. This is the inverting terminal. The non-inverting here, the positive is the non-inverting. So if you apply your signal in the non-inverting, the positive, then you get your output in amplified fashion but not inverted. it is in phase with the input terminal. So that is the difference. So those are the configuration of the open loop configuration, and usually they have some limitations. There is usually clipping of the output waveform when the output waveform exceeds saturation levels, and this is due to the very high gain of the operational amplifier. Remember, in the ideal characteristics, in the ideal voltage transfer characteristic, we had drawn something like this. Voltage increases as you increase VID, these are the out. So once this reaches saturation, even if it was a sinusoidal signal, it will be forced to go flat like that. So it stays at saturation irrespective of the increasing VID. So that means that if it was a sinusoidal signal like this, that means that if it was a sinusoidal signal like this, then there will be clipping. And whatever you get at the output will be something like a rectangular. That is not a replica of the output. So there is usually clipping. So this portion will be clipped when the output voltage exceeds the saturation levels. And we are saying that is due to the very high gain of the op-amp. Limitation number 2 is that signals with low magnitude, that is in the order of micropods or even less, and of very low frequencies, can be amplified accurately without distortions. So such signals are susceptible to noise, and they are also not easy to obtain in the lab. Number 3, limitation number 3 is that open loop gain is not a constant, and you find that it changes or it varies with changes in temperature and also power supply. Then bandwidth of limitation number 4 is that bandwidth of most of the open loop op-amps is also negligibly very small, which makes them unsuitable for AC applications. Though you can also you can find such configurations being applied in areas like mat vibrators, square wave generators, those non-linear applications. But with the linear applications, it cannot do well. So that is open loop configuration. Number B is the, or rather number 2 is the closed loop configuration. In the closed loop configuration, we usually have the inverting amplifier and the non-inverting amplifier. Again, we can have the circuit here. That circuit here represents the inverting amplifier. That is closed loop configuration of the inverting amplifier. When you're talking closed loop is the op-amp with feedback. Feedback is whereby you get a fraction of the output and take it back to the input. So here we have a resistor, R1, and the feedback resistor here is RF. So that is the closed loop configuration of the inverting amplifier. Remember, we are applying inverting amplifier in the sense that we are applying our signal to the inverting terminal. So you apply your signal here like this. You expect it to be inverted or out of phase with the input signal, but in the amplified fashion. Next, we have the non-inverting amplifier. The non-inverting amplifier we are having, I can draw it here. In the non-inverting, you apply your signal to the non-inverting terminal, which is the positive. Then here, you still retain your R1 and your feedback. Remember, it's a closed loop, so we should retain our feedback here network, which consists of RF. Then this terminal here is grounded like that. So you are applying your input at the non-inverting terminal. The other terminal is grounded. Your feedback remains. So that is the diagram for the non-inverting amplifier in closed loop configuration. Now we look at operational amplifier applications. Now, op-amp finds a wide range of applications. Remember, when we were defining, we said that you can have external resistors, capacitors connected, or even both, to suit a particular application. These are not inside, for example, this resistor and this resistor are not inside the op-amp itself. They are connected externally. So we are saying you can connect the operational amplifier with external resistors, capacitors, to have various or to suit various applications, such as what we are going to see. So number one, it can be connected as a constant gain amplifier. And as a constant gain amplifier, you can either have the inverting amplifier or the non-inverting amplifier. But before then, I want us to look at the concept of virtual ground using this diagram of inverting amplifier. I can just go to our, can redraw the diagram here. Have my feedback resistor connected there. So this is inverting, yeah? This is number A, inverting. What I want to explain is the concept of virtual ground. Virtual ground. What is virtual ground? Now, we said that if you apply a signal at the inverting terminal, it will appear at the output as in the amplified fashion, but out of phase with the input signal. That is inverted, and that's why we call this inverting, because it inverts. So we have, this is input, at the output we have our signal there, which is inverted. Now, this is negative feedback, and it means that it's a negative feedback, and it means that you take a fraction of the output and take it back to the input here. So we are having V in as our input voltage here. Let's assume this is our V out. We call this our V out. We call this our RF, the feedback resistor RF, then R1 here at the input. Now, when you apply V in, let's call this point A. When you apply voltage V in with a sinusoidal, let's assume it's a sinusoidal signal like this, this point A is brought into a positive potential. This point here is brought into a positive potential. Remember, this is inverted, so we get an output, which is out of phase with the input. So with the feedback, we are taking a fraction of the output here is taken via this network, feedback network to the input, all right? So it is taken via this network here to the input. So at the moment you apply V in, this gains positive potential, and at the same time, V out, the feedback voltage, V out, we can say beta, V out, where beta represents our fraction of output voltage, is taken back to the input. So if you apply V in, feedback voltage here is brought into existence. So because this is out of phase, the feedback voltage is out of phase with the input, then it means that V in that will be at this particular point will reduce. And at the instant, or rather at the moment, when V in becomes exactly equal to the negative feedback voltage here, or rather the feedback voltage, then they cancel out and the voltage here will attain a zero potential. The voltage there will attain a zero potential, and once it attains that, that's now what we call the virtual ground. It's like it's like we are having a ground here. The reason as to why we call it a virtual ground is because you see this at the non-inverting terminal we have ground. So the reason as to why we call it virtual ground is because it's like there is a short between this terminal, that is the inverting, and the non-inverting. But despite the existence of that short, there is no current that flows between the two terminals, and that's why we call it a virtual ground. That's why we call it a virtual ground. Okay, now we can now come back to our inverting amplifier. Inverting amplifier is the one that provides an output voltage that is proportional to the input multiplied by a constant. So we can still use this diagram here. We say here there is an input current I in. And because by the fact that this is a virtual ground, we also expect a current here to flow. We can call it IF on this particular branch here. So that we have our I in is equals to V in over R1. That will be our current. The current IF will be equal to V out, because actually this voltage V out is the voltage that will appear between this particular point and this point here. So our IF, or the feedback current, is equals to negative, because it is a current that is flowing in the opposite sense, minus, sorry, IF is equals to V out divided by RF. So basically, these two, you can equate them and say V in over R1 is equals to V negative V out over RF. Because actually this point here is a summing point where these two currents will come and cancel out so that we get the virtual ground. So they should be equal. That is I in is equals to IF. So that is actually what we are doing here. So V in over R1 is equals to V out. We can rearrange this and have RF over R1 is equals to negative V out over V in. This can be written as, we take this negative to this other side, so that we have V out over V in is equals to negative RF over R in. But then we know our V out, this is equals to our gain. So AV, which is our voltage gain, is equals to negative RF over R in. And actually that is what we are having here. The gain of the the gain of the inverting amplifier can thus be expressed as voltage gain is equals to negative RF over R1. So from this expression, you can see that the gain of the amplifier does not depend on frequency, does not depend on the other parameters of the amplifier, but depends on the external, the feedback, which is a network of resistor alone. So the gain is expressed as RF over R1. The gain of the inverting amplifier is expressed as negative RF over R1. And therefore, if for example, you had been given V in is equals to, for example, 1 millivolts, you're given the value of RF, let's say, for example, 1 kiloohm, 1 kiloohms, or rather, let's say, for example, to be precise, 10, and then R in 1 kiloohms, then it is possible to get our gain. Our gain will be expressed as it's actually possible to get our gain, which is expressed as RF over Rin. And then we have that negative, which can be given as 10 times 10 raised to 3, of course, because it is kiloohms, then over 1 times 10 raised to 3. So our gain here will be 10. So if our gain is 10, and assuming you've been given V in as 1 millivolts, assuming you had been given V in as millivolts, and you are told to get V out, then comfortably you can say V out is equals to our gain times V in, of which our gain we have is 10, then times 1 millivolt. So the output will be 10 millivolts. So you can comfortably get that. So the most important thing is to note that our gain in an inverting amplifier is given by negative RF over R in. So next we have the non-inverting amplifier. So with the non-inverting amplifier, you can see here we have applied our voltage to the non-inverting terminal. So it means that at the output, the signal will not be inverted. It will be a replica of the input, but it will not be inverted. It will be in phase with the input signal. We have our feedback resistor to provide our feedback voltage, then our input resistor here. So again, for this, we can also have the voltage gain is usually given by 1 plus RF over R1. So we can redraw the circuit here, just for the sake of explaining. So this is V1, this is V out, we have RF and then R1. Now, we have current here, we can call it I in, and also the other current as a result of V out, which you can call it IF, Now, our current I in is equals to V1 over R1. Our current is equals to that. I in is equals to V1 over R1. And because this is our summing point, we can also express the current on the other side, which can be written as IF is equals to output voltage V out, then divided by, from this point, if we had a resistor there, would say that if this was output voltage appearing across here, this would be like in parallel with from this point up to this particular point ground here. So our V out will be equal to our IF is equals to V out over R1 plus RF. So because this is the summing point, we can sum the two and say our I in is equals to IF, which can also be written as V V1 over R1 is equals to V out over R1 plus RF. If you rearrange this again, you can have, we rearrange this, we can have V out over V1 is equals to R1 plus RF over R1. This can also be rewritten as V out over V1 is equals to 1 plus RF over R1. But then we see this is our gain, AV. So our gain will be equal to 1 plus RF over R1. So that gives us the voltage gain of the non-inverting amplifier, which is given here. So again, we can see that the gain depends on the feedback resistor and R1. So application number 2 is the differentiator. And a differentiator is a circuit that will give an output voltage that is proportional to the rate of change of the input voltage. A differentiator gives an output voltage that is proportional to the rate of change of the input voltage. So from this expression here, remember we are having, this is the circuit for a differentiator. So at the input here, we are having a capacitor. Then we also have our feedback resistor. So as Vin increases, Vin increases, the voltage across the capacitor will also be increasing. Voltage across the capacitor will also be increasing. And therefore, because we know charge is equals to IT, therefore we can express I as equals to Q over T. And we know that Q is equals to CV. So that's why we have in our equation here, IC, the current through the capacitor is equals to C V. Actually, this represents our charge. We are talking about dV in because the voltage is changing with time. So that's why we are having actually this. Time is changing, voltage is also changing, because Q is equals to CV. So our IC is equals to CV dV in over dt. And because this is our summing point, this point here is our summing point, then that current will be equal to IF, of which our IF is equals to negative V naught over RF. Negative because the IF is in opposite direction, or is as a result of the voltage that has been inverted. So when we rearrange this, then you will get your V naught as equals to negative CR dV in over dt. So from this expression, we can comfortably say that the differentiator provides an output which is proportional to the rate of change of the input. This is our input here. So the rate of change of input multiplied by a constant. And that constant actually depends on the value of the capacitor and also the value of the feedback resistor. So that is the differentiator. Another application is the integrator, and an integrator is the one that provides an output which is proportional to the integral of the input voltage. So with the integrator, this is the circuit diagram. Here we have a resistor, and at the feedback we have a capacitor instead of a resistor. Remember we said that you can configure using resistors, capacitors, or even both to get or to suit a particular application. So for an integrator, you have a capacitor. So again, the current I in here is equals to V in over R in. For IC, the current IC, because at this particular point here, we are having V naught. This V naught is the one that will appear across the capacitor, having this as a virtual ground. So V naught here is the one that appears across the capacitor. So that we are saying, that's why we're saying IC is equals to negative C dV naught over dt. So if you rearrange, then you will find, and if you rearrange and make V naught the subject of the formula, then V naught is obtained as equal to negative 1 over CR in, then integral of V in dt. And we can comfortably say that our integrator provides an output which is proportional to the integral of the input, but of course multiplied by a constant. And that constant depends on the value of R in and also the value of the capacitor. Next, we have a summer. And a summer is the one which, or we can call it a header, the one which provides an output voltage which is proportional or equal to the algebraic sum of 2 or more input voltages. So, for example, here we have a 3-input summer. We have V1, V2, V3, and for each of the inputs, we have a resistor and one feedback resistor here. So again, these the currents I1, I2, and I3 will sum up at this point here. So that we can say our total current I here will be equal to I1 plus I2 plus I3. But that current should be equal to the feedback current because this is our summing point. So that's why we're saying IF, this one, is equals to I1 plus I2 plus I3. And we know that our IF, the feedback current, obviously equals to V naught, output voltage divided by RF, with a negative, remember, because of the inverting, because our signal is applied in the inverting. So we have a negative V naught over RF. So that is our IF. So this current IF should be equal to I1 plus I2 plus I3. This is I1, which is V1 over R1, I2, which is V2 over R2, then I3, which is V3 over R3. So that if you rearrange and make V naught of the V naught or output voltage the subject of the formula, then this is the expression that you get. This is the expression that you get. But if you are to arrange the if you are to rearrange the expression, you can have V naught is equals to RF over R1. Of course, this is a negative, plus RF over R2 plus RF over R3. Then this multiplied by V1 plus V2 plus V3. If you were to rearrange this expression, that is what you would get. And if R1 is equals to R2 is equals to R3 is equals to R, then this expression would become V naught is equals to negative RF over R, then V1 plus V2 plus V3. So from that you can see that the output, if the three input resistors were the same, then you would have something like that, this negative RF over R, V1 plus V2 plus V3. which means that now our output voltage is actually an algebraic sum of the 3 voltages, of course multiplied by a negative scalar. Of course multiplied by a negative scalar, which depends on the values of RF and R. So that is the adder or the summer. Then lastly, we can also look at the filters, though we have so many applications, can configure the op-amp into so many applications. We have the high pass filter and the low pass filter. So the gain of the op-amp is it's actually equal to a ratio, as we've seen from the inverting and the non-inverting amplifier. It's actually a ratio, and these ratios are actually from 2 external impedances, and by proper selection of these impedances, an active filter can be constructed. An active filter can be constructed, and I'm just giving an example of high pass filter and low pass filter. Can start by the high pass filter. With the high pass filter, just giving a simple diagram here, just to explain the concept. We have our negative, our feedback resistor RF remains. We have R1. We can have this capacitor SC. So with the high pass filter, it's actually a circuit that will allow signals with frequency above a specified cutoff frequency to be amplified, and will greatly attenuate any signal that is not within that signal frequency, or that is not, or that is below the cutoff frequency. This is what we mean for an high pass filter. You find that from 0 up to a particular cutoff frequency, any signal above that cutoff frequency is amplified. So this part we call it a pass band. Any signal below the cutoff frequency will be attenuated. So this we call it the attenuation band. So any signal above here is amplified. Any signal here between 0 and the cutoff frequency is attenuated. So let's see how now this works. We know that for a capacitor, capacitive reactance is usually given by XC, 1/2 pi FC. That is capacitive reactance. So for very low frequencies, if F is very low, we can just approximate 0 for the purposes of understanding. So if XC is 0, then it means that XC goes to infinity, or it becomes very high. If F is low, it means that XC is very high. So it means that signals with the low frequencies, they will not be allowed to pass, and therefore at the output there is no amplification. There is no voltage at the output. The signal will not be allowed to pass with low frequencies. Now with high frequencies, XC again, you can say it's 1/2 pi FC. With high frequencies, if F is high, it means that capacitive reactance XC is low. So if XC is low, then it means that it will act as a short, and it will allow those frequencies to pass, and the circuit will behave like a normal inverting amplifier. So that's how the high pass will allow frequencies of high frequency signal, but attenuate or reject signals with low frequencies. Okay, next we look at low pass filter. This kind of a filter will amplify signals with frequency below a specified cutoff frequency. So we can have a diagram here for a low pass filter using the op-amp. So at the feedback here, we have a capacitor and a resistor. Capacitor is there and a resistor. And then we apply our input signal at that particular point, that is the inverting, and then the other point we ground. And we are saying it will amplify signal up to a specified cutoff frequency, that is from 0 up to maybe a specified cutoff frequency FC. So between 0 and FC, all these signals will be amplified. But any signal that is above the cutoff frequency will be greatly attenuated. Now, to explain the working of this, know that our capacitive reactance XC is usually given by 1/2 pi FC. So at high frequencies, F, which stands here for frequency, is high. So if F is high, it means that our XC will be very low. It will be very low. So if XC is very low and we apply our input signal here, our capacitor here, C, our capacitor C will act as a short. And that means it bypasses R. So if it acts as a short, then it means that our Vin will not be amplified. That is for high frequencies. High frequencies. So any signal with high frequencies, XC is low, it acts as a short, and therefore our input will not be amplified because this is bypassing our R. And remember, our gain is usually given by RF divided by Rin. So we will not have any output voltage. Next, if on the other hand, if our frequency is low, if F is low, XC will be very high. So if XC is very high, that is the capacitive reactance, then it means that this particular point here, at the terminals where we have connected the capacitor, it will appear as an open circuit. So if this particular point appears as an open circuit, then our R here is brought into existence, and then the circuit will behave like a normal inverting amplifier, and therefore it will give an output, and there will be some gain. So that is how our low-pass filter will allow signal with low frequencies, but reject signals with high frequencies. So in summary, you can see that a large number of operational amplifier ICs are available to suit every suitable application, from standard bipolar precision to high speed, low noise, high voltage, etc. So op-amps are available in IC packages of either single, dual, or quad op-amps within a single device. When we talk about single, we are actually meaning that one single op-amp is inside that particular IC package. When we talk about dual, it means that there are two. Quad, it means that there are four in one single chip. So the most commonly used is and available of all operational amplifiers in basic electronics kits, and also in projects is the industry standard microamp 741. To finish with, that is just an example of a single op-amp which is, or rather in that particular chip, we only have a single op-amp, which has the respective input terminals, output. We have the positive supply terminal input offset. We have the output, the negative supply bias terminal, the non-inverting, inverting, and also the input offset. So this gives, it's just an example of an operational amplifier giving its the pin configuration, the 7-port 1 op-amp pin configuration. That marks the end of our lesson. Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.